Hi, we are AGH Space Systems, a team from AGH, University of Kraków, Poland. Our rover, Kalman, is a continuously evolving platform maintained by us for over 7 years now. Our team is made up of students with expertise in fields ranging from robotics and computer science to chemistry and geology. We work in 4 specialized subteams: mechanics and electronics, software and science. Together, we're thrilled to present our preparations for the University Rover Challenge 2025.
Kalman's chassis is a welded aluminum frame. It has extension slots for mounting rods at every corner, which are designed to carry mission-specific equipment, like cameras, status LEDs, communication transceivers, and many more. The chassis is mounted on a 4-wheeled, rocker-only suspension.
Each wheel has independent steering and propulsion, which enables harmonic locomotion. The rover can drive forward, sideways, or diagonally, and is even able to rotate in place. The tires are airless and we 3D print them with a gyroid shock-absorbing infill.
The robotic manipulator has 6 degrees of freedom, which enables us to collect samples, lift objects to great heights, and to execute complex maintenance procedures. It is designed with modularity in mind, hence we're able to easily swap end effector claws for mission-specific variants. Additional tooling or cameras can be attached on demand and the whole arm can be dismounted from the chassis.
Our power delivery system uses 6S lithium polymer batteries that are hot swappable. They slide in and out of 3D printed mounting outside the frame. There is an easily reachable emergency stop button which physically breaks the connection to the batteries, completely shutting off the power. Remote communication is managed using half-duplex RF modules. Video is provided by regular analog cameras and a high-quality digital camera mounted on the arm. Our testing has demonstrated reliable control over the rover at distances reaching 1 km with minimum video latency. All the essential PCBs are designed with uniform physical dimensions, sliding seamlessly into a single backplane cage. We call this design MINE AGH. Its modular design enables quick and efficient loadout changes, allowing us to switch between maintenance and autonomous missions in under 10 minutes.
Kalman's surveying capabilities are complemented by a drone designed for aerial reconnaissance. Powered by custom-made Lion battery pack, the drone boasts 14-inch carbon props and 650 mm off-the-shelf frame, which allows it to sustain continuous flight for over 20 minutes, even while carrying the dummy mass. It has a GNSS receiver, optical flow, and a LiDAR sensor for localization.
In order to drive, the operator can use a custom-made wheel controller with more precise analog sticks and knobs. The end effector of our robotic arm is controlled using a space mouse, where inverse kinematics are used to steer individual joints. The operator can also initiate an automatic return to one of many predefined poses.
The autonomous localization system uses a dual EKF configuration. We use one filter to measure local odometry readings and another one to fuse global corrections. Local filter takes visual odometry data from 4 depth cameras and rotation changes from the IMU. Global filter uses SLAM, GNSS, or detected fiducial markers to provide world reference positioning.
The depth cameras aren't only used for localization. They output point clouds that Kalman uses to detect obstacles by analyzing the slope of the terrain. Those obstacles are then accounted for by NAV2, which controls the rover. The framework is configured to use our custom path follower plugin that takes advantage of Kalman's holonomic locomotion capabilities.
We've developed a custom robotic simulation in Unity engine, where we can achieve higher fidelity and leverage C# scripting capabilities to implement interactive testing environments. Moreover, we perform real-world testing on a weekly basis in months leading up to the competition to ensure our system works under the expected conditions.
An onboard mobile laboratory enables us to test soil samples for the presence of life. It is the home of several science instruments: an ultrasonic chamber, a biomarker spectrophotometer, and a fluorescence analyzer. This provides spectral data with DNA, amino acids, carbohydrates, and chlorophyll content, which together indicate whether life is present in the soil.
All the imported subsystems of our rover are being thoroughly tested under relevant conditions. In addition, we perform regular simulations of the challenge tasks, which allows our operators to perfect their skills well before the finals in Utah. None of this would be possible without support from our university, private sponsors, and the Ministry of Science and Higher Education. Thank you and see you in space.